I'm Anuradha Mathur. I teach physics at Modern School, Vasant Vihar, New Delhi. Today we will be talking about the magnetic field associated with the Earth. It has been long established that the magnetic field around the Earth can be experimentally determined, accurately measured, and we are going to see how some of these relevant and important elements are found and defined. Let us consider the globe. It's a toy globe, and we are going to see how how do we talk about different portions and positions on the Earth. And if you can see here, there are latitudes and longitudes marked. So, it is easy to talk about a location in terms of the longitude passing through the Greenwich. All these are marked as east and all these are marked as west, and the equator, the axis of rotation of the Earth is inclined at a particular angle. These things are known facts, geographically established facts. Pictures from the space have shown that the axis is inclined. How do we know that there is a magnetic field associated with the Earth? We have a freely suspended magnet, and if we ever were to keep it in a way that it is ready to move about a vertical axis, as in this case, it will always rest in the north-south direction. This north-south direction is associated with something inside this. That means, we imagine a dipole to be inside the Earth. The dipole, where are the poles associated with this? Some of the known facts about the Earth's magnetic field are that the south of the dipole imagined inside this is somewhere in the northern section, that means somewhere over here, and the associated north pole of our magnetic dipole is towards the south. Where exactly this is has been seen by study of field lines, and it is found that the magnetic south pole lies somewhere in northern Canada at a location marked here, which is 79.8 degrees latitude and about 71.4 degrees west longitude. So, somewhere around here you will have the pole. That means, not exactly coincident with the geographic north, which would be passing through the axis here. Some more facts known about the magnetic dipole inside the Earth are that it has a dipole moment of around 8 into 10 to the power of 22 ampere meter square, and the dipole axis is obviously inclined, joining the two magnetic poles here to the axis of rotation, and this angle has been found to be 11.3 degrees. Also, on the surface of the Earth somewhere you find that the magnetic field has been obtained somewhere around 10 to the power minus 4 Tesla. What causes the Earth to have a magnetic field? For a long time it was thought that there was a magnet inside it, but that original thinking is now redundant, and conventionally today what we think about the magnetic field, we say it is due to the movement of molten fluid inside it, and so the convective currents that are in it, fluids such as molten iron, molten nickel, and that is what is said to be responsible for Earth's magnetic field. Having said that the Earth's magnet inside the magnetic field is generating the two poles, so it is a dipole. Can we estimate the value of its magnetic moment? Well, sure we can, by using our old expressions that we have been using for magnetic dipoles or current carrying loops. Let us see how we can do that. Let us do this estimation by saying that at the equator the magnetic field is 0.4 Gauss and the radius of the Earth is 6.4 into 10 to the power of 6 meters, and using our expression which we used for the dipoles earlier, mu naught m upon 4 pi r cube, we get this value for m to be equal to 1.05 into 10 raised power 23 ampere meter square. This value is consistent with the value that has been experimentally determined, which comes out to be approximately 8 into 10 raised power 22 ampere meter square. This consistency not only establishes that we have to take and treat the Earth's magnetic field as on account of a dipole, even though there is no magnet inside it. So, let us now look at other factors which are necessary for its description, and before we do that, we are going to do some definitions. Definitions of the type that we are going to talk about the geographic axis as the line joining the north pole and the south pole as geographically established. We are going to talk about a magnetic axis as the line joining the magnetic south pole and the magnetic north pole over here. We are going to talk about a geographic meridian, which would be a plane passing through this axis. So, at a location the geographic meridian would correspond to the longitude passing through the axis. So, a plane of this order. So, for every latitude you can imagine a geographic axis passing through the axis of rotation and the location at that point. What would then be the magnetic axis? This magnetic axis would be the line joining the magnetic dipole and a plane passing through that. So, you have a magnetic meridian at a location to be given in terms of, supposing I want to find the magnetic meridian in Delhi right now here in the studio. So, I put my freely suspended magnet. This is going to rest in response to the Earth's magnet, and the line joining this is going to be along the line of the magnetic axis of the Earth. So, the plane passing through this is going to contain that axis as well as the axis of this freely suspended magnet. This now becomes the magnetic meridian. We can also be talking about the equator. The geographic equator, as we have seen, is this circle which is along the center of the globe. And if I take a plane perpendicular to the axis of rotation at the center, it would be passing through the geographic equator. Likewise, we can imagine and talk about the magnetic equator as well. These are important and relevant definitions, because we are now going to be describing the elements of Earth's magnetic field. There are only 3 elements or 3 requirements to talk about the Earth's magnetic field at a particular location. First one is angle of declination. This angle at a location is the angle between the geographic meridian and the magnetic meridian. If you look at it like this, that if I mark a plane and this plane is showing me the geographic meridian, and making an angle with it is a magnetic meridian here like this. This angle is my angle of declination. Why is it relevant? Because declination is going to become greater and greater as we go towards the north pole or towards the south pole. At the equator, it is minimal. Now, talking about angle of declination, first let us see how we can show it. Supposing I take a section and mark the slice from the center of the globe, and I have a north and a south here, which is my geographic axis, and supposing I also mark on it my magnetic axis, and I talk about the plane containing the two. So, it will be something like this. So, the angle between these two planes the blue plane showing the magnetic meridian and the yellow plane showing the geographic meridian. This angle is angle of declination. As you can see from here, this value of angle of declination is smaller near the equator and it becomes larger as we go along higher in latitude. In Delhi, its value is only 0.1 minutes, not even a degree. But as you go closer to the poles, this value becomes higher and higher, 11.3 degrees, which is huge. The next element to be looked at is angle of dip. Now, we are going to be talking about a magnetic needle which is capable of moving about a horizontal axis. That means, it is capable of moving like this. Now, if you talk about a needle which is allowed to do so, you can have random variations, and wherever it will stop you will say, okay, this is another option, this is another option, but that is all irrelevant. What we are going to see is the dipping angle of this needle in the magnetic meridian. So, for that let us first establish using this compass needle here, establish the magnetic meridian, which is this plane, and there is a special apparatus called the dip circle. It looks like this. It's got a needle, and as you can see, this is its axis of rotation. So, it's pivoted along an axis like this, all enclosed in a glass chamber only to keep air off from it. It is marked, there are markings all along here. This would be 0, 0 and this is 90. The beauty of this apparatus is that you can adjust it by moving it along a vertical axis, adjust it so that this frame lies in the magnetic meridian. Now, the needle will stop at a particular location on the surface of the earth, depending upon where it is, depending upon the latitude, depending upon the value of the earth's magnetic field there, and it will rest in the direction in which the magnetic field is. Now, the angle that the horizontal, you consider this horizontal in the magnetic meridian, the angle made by this needle in the magnetic meridian with the horizontal, this is known as angle of dip. If you have understood well, this angle dip is going to vary from place to place. It will be 90 degrees at the magnetic pole, that means whether it is the magnetic south or magnetic north. It will be 0 degrees at the magnetic equator, and for all other positions this will be some other value between 0 and 90. So, at the poles, if I were to take my dip circle, it would rest like this. I can make it do that here, because in the studio it is influenced by Earth's magnetic field in Delhi, and therefore, this cannot be shown that this will become vertical or it will become horizontal. You will have to think about how you can show it as horizontal in the lab experimentally, and it can be done. What do we use this angle of dip for? We can find the value of Earth's magnetic field at a location. How do we do that? We can find the horizontal component by any of the methods using field lines, placing them on a board on a horizontal table, finding a neutral point and calculating the value of horizontal component of Earth's field. Now, what is important is that how do we use the angle of dip and what do we use it for? Finding this value of total intensity, vertical component is here, horizontal component is here. This is my magnetic meridian, this plane, the needle here. This is geographic meridian, the angle between these two is your angle of declination. We are making no use of that for calculation of the total intensity of Earth's field. The angle of dip is important, that is the angle that you can see here, and that will give us the vertical component V to be equal to f cos theta, where theta is the angle of dip, and the horizontal component h would be f sin theta, which will be again established from the angle of dip, or we can say tan theta or tan of dip angle is the ratio of vertical and horizontal components. You can get the value for total intensity I. This value of total intensity on earth at a particular location, say Delhi, we can take the value is 0.36 Gauss. At other locations it would be different, as you can see, because angle of dip would be different. So, three elements of Earth's magnetic field are angle of declination, angle of dip, and horizontal component of Earth's magnetic field. So, let us sum up some facts about horizontal component of Earth's magnetic field. For one thing, it will vary from place to place, angle of dip is varying. Then it is going to be equal to the total intensity of Earth's magnetic field at the equator, angle of dip is equal to 0. So, today you have learnt the three elements of Earth's magnetic field: angle of declination, which was the angle between the magnetic meridian and the geographic meridian. Then you learnt about angle of dip, which was the angle made by a magnetic needle in the magnetic meridian with the horizontal. And you also learnt about the horizontal component of Earth's magnetic field, and these three elements can easily describe all the requirement for knowing how much the Earth's magnetic field is affecting anything that we are doing on the earth.